In our example, we've seen what a risk-averse utility function looks like. Now I'd like to show you how to incorporate different risk preferences into our model of utility. So just to review, when we have diminishing marginal utility, then this represents risk aversion. Our utility function is concave, and that means that when we have a lottery, okay, we have, say, two potential outcomes and some probability that each occurs, then the utility of the expected value will be greater than the expected utility. So let's write that out. So here we have the payoff from expected outcome 1 and the payoff from expected outcome 2. And then in the middle, some expected value of the lottery. Here, along this line representing the lottery, we get the expected utility of the lottery. And up here, we have the utility of the expected value of the lottery. So you can see that my expected utility, which is really what we make decisions on, is smaller than the utility of the expected value. So this is risk aversion. And this is typically what we assume our utility function looks like for the reasons that we discussed in the first part of the class. And of course, this means that people dislike risk. We get value from certainty or reducing risk. All right, so that's similar to the example that we just looked at. We can also model a risk-neutral utility function as having a constant slope. And here we could think about a similar lottery where we have two outcomes with some expected value. And so here you see that the lottery line is equal to the utility function. So our expected utility is equal to the utility of the expected value. They're the same. All right, so here all we care about is expected value. We'll choose the option with the highest expected value. We don't care about risk. Now, there's another option, and some of you may have looked at the initial question about the jobs and thought, I would rather take the job at the startup because there's a potential big upside, right? And in this example, that would be characterized as risk-loving behavior because you're Well, actually, you could even take that option if you're risk averse because there was a higher expected value. So, or risk neutral, right? But in some cases, people might even be willing to give up money in expectation in order to take on risk. So, that an example of that would be playing the lottery, right? Or going to a casino to gamble, because in expectation, you're going to walk out with less money than you walked in with, but there is a chance that you could win some high amount. And so sometimes people exhibit risk-loving behavior. In general, people exhibit risk-averse behavior, but different people have different preference for risk. So we can model risk-loving behavior with a convex utility function. And here you can see if we have a lottery with our two different outcomes, that the expected utility is actually higher than the utility of the expected value. Right, so maybe you're going to pay that $1 for a lottery ticket because it's just $1 and you have a small chance of winning a large amount of money. All right, so this is the expected utility. And this is the utility of the expected value. So our expected utility here is greater than the utility of the expected value. That means that we're actually willing to give up some value in expectation for risk, right? Or risk loving. All right. Good. So we see how the different types of utility function can help us model different behavior under different circumstances. And there are some other ways of conceptualizing decisions making risk, which we are not going to get into during this lecture. But I think that this is helpful for at least beginning to understand how we think about these problems. Okay, so then the last part of the example that I want to explain here is that we can actually then look at this situation that we've mapped out, and we can characterize not just how much utility we get from different circumstances or which circumstance we prefer, but we can think about the value of risk in this situation, okay? How much does this individual value the risk that comes with the uncertainty of the startup job? And we can do that by looking at what we call the certainty equivalent. What amount of money with certainty is equivalent to the expected utility from the startup job, right? So you can see that here on our graph. You can see that the startup job gives us an expected utility of $197. So we want to know what amount of money with certainty will give us that same utility. Okay. So what amount of money with certainty yields the same utility as the lottery? All right, so the lottery gives us 197 utils, right? And so we just need to solve for I in this equation, and we get that I is equal to about $39,000. I have done some rounding in the numbers I've written down in the problem, but yeah, we get basically $39,000. So that number here on our graph is $39,000. Okay, all of these are in thousands. And then that's our certainty equivalent. Okay, so our certainty equivalent is 39,000. And then, like I said, we can actually look at the amount of money that this person is willing to give up in expectation in order to reduce risk. So this distance here between the expected value of the lottery and the certainty equivalent is what we call the risk premium. It's the value of the risk or the disutility from the risk, right? This person is indifferent between $39,000 with certainty and $55,000 with risk. So the value, the disutility that they get from that risk is equivalent to $16,000. Okay. All right, so our risk premium equal to 39,000, oops, 54,000, or sorry, 55,000 is our lottery's expected value minus 39,000. So we get $16,000. That is the disutility you get from the risk, or in other words, the amount you would be willing to pay to reduce risk. Okay, to eliminate your risk.